Imagine a world not so long ago, a mere 20,000 years in our planet's cosmic calendar. This was Earth during the last glacial maximum. Global temperatures were a chilling 10 degrees Celsius cooler than they are today. Vast sheets of ice, some up to 3 kilometers thick, smothered much of the northern hemisphere. The Great Fennoscandian ice sheet stretched from Ireland all the way to eastern Scandinavia, locking away a colossal amount of the world's water. This was a profoundly different planet, a world of ice and stark, frozen tundra, where familiar coastlines simply did not exist. With so much water frozen solid in these immense glaciers, global sea levels plummeted. The oceans receded by as much as 120 meters, a staggering drop that revealed vast new landscapes. The seafloor became dry land. What we now know as the English Channel was not a sea at all, but a wide, cold valley. Great Britain was not an island but a peninsula, a finger of the European continent. This exposed land bridge, known as Doggerland, connected the landscapes of ancient Britain and France, creating a continuous plain that would soon become the cradle for a river of immense proportions. As the climate began its slow, inevitable warming, the great ice sheets started to melt. Torrents of meltwater poured south from the glaciers covering Britain and Scandinavia, and north from the thawing Alps. This water needed somewhere to go. It began to carve its way across the newly exposed European plains, following the path of least resistance. This was the birth of a ghost river, a temporary titan of geology, known today as the Channel River. It was a river system that appeared and disappeared with the pulse of the ice ages, a recurring feature of our planet's dynamic climate system. The formation of this mega river was not a singular event. It was a cycle repeated over millions of years. Geologists believe the Channel River system emerged during at least 5 of the last 10 ice ages, each time a slightly different version of the one before. During the long, cold periods, which could last for up to 100,000 years, the river would shrink to a mere trickle or vanish completely, its bed frozen and dormant. Then, as the planet warmed once more, the ice would retreat, and the river would be reborn in a spectacular deluge, reshaping the continent with its awesome power. This was no ordinary river. The Channel River was a true behemoth, a confluence of many of Europe's greatest waterways. Imagine the ancestors of the rivers we know today, the Thames, the Rhine, the Seine, the Somme, and even the Elbe, not flowing to separate seas, but merging into a single, unified system. These ancient rivers all became tributaries, feeding into one gargantuan trunk that flowed through the heart of the Channel Valley. This liquid superhighway gathered water from an enormous area, creating a drainage basin of truly continental scale, a system unlike anything seen in Europe before or since. The sheer scale of this prehistoric river system is difficult to comprehend. At its peak, the watershed of the Channel River spanned an incredible 1.2 million square kilometers. To put that into perspective, that is a drainage area comparable to the modern-day Mississippi River system in North America. It stands as the largest single river basin in the entire geological history of Europe. During the most intense periods of glacial melt, scientists estimate its outflow could have been truly staggering, potentially reaching a volume twice that of the modern Amazon River during its flood season. It was a force of nature on a planetary scale. You might expect such a powerful river to carve a deep, Grand Canyon-like scar into the landscape. Yet the geological evidence on the continental shelf is surprisingly subtle. The river did not leave the deep gouges one might predict. The reason lies in a series of huge buffer lakes that formed in the low-lying basin of the modern North Sea. These vast, placid bodies of water acted like settling ponds. As the rushing meltwater entered these lakes, its velocity slowed dramatically, causing the abrasive sand and gravel it carried to drop to the bottom long before reaching the main channel. This interconnectedness of ancient rivers has left a curious and lasting legacy, a biological puzzle that baffled naturalists for centuries. It explains why we find the exact same species of freshwater fish, like pike and roach, in rivers that are now completely separate and isolated by salt water. The fish in the River Thames in England are genetically related to those in the River Rhine in Germany. They are descendants of a common population that once swam freely throughout the vast, unified network of the Channel River, a living echo of a lost aquatic world. The existence of the Channel River had consequences that stretched far beyond the borders of Europe. The immense volume of water it channeled from the melting glaciers had to go somewhere, and its ultimate destination was the global ocean. This single river system was a primary contributor to the dramatic rise in sea levels that marked the end of the last glaciation. As the Channel River poured trillions of tons of fresh water into the Atlantic, it is believed to have been responsible for a significant portion of the total sea level rise, contributing as much as 20 meters, all on its own. As the glaciers continued their retreat about 15,000 years ago, the geography of northern Europe began to transform once more. The meltwater that had once flowed south to feed the Channel River started to pool elsewhere. It became trapped behind high ground in the Baltic region, blocked from reaching the ocean. This process initiated the formation of a series of massive proglacial lakes. Over time, these lakes merged into one gigantic freshwater body known as Ancellus Lake. This prehistoric lake was significantly larger than the modern Baltic Sea, a vast inland sea of meltwater covering much of Scandinavia. The story of the Channel River is ultimately a story of its own demise. As sea levels continued their relentless climb, the Atlantic Ocean began to push eastward. It crept up the river's own valley, slowly but surely reclaiming the land that had been exposed for millennia. The wide, cold plains of Doggerland were inundated. The land bridge connecting Britain to Europe was severed, and Britain became the island we know today. The great river was drowned by the very ocean it had helped to swell, its valley transformed into the English Channel, its mighty current replaced by tidal flows. Eventually, Ancellus Lake also found its connection to the rising ocean. Salt water surged into the vast freshwater basin, transforming it into the brackish Litorina Sea, the direct ancestor of today's Baltic Sea. Even with global sea levels similar to our own, this ancient sea was about 25% larger than the modern Baltic. The final disappearance of the Channel River and the flooding of the continental shelf marked the end of an era, finalizing the map of modern Europe and setting the stage for the next chapter in the continent's history. The melting of the ice sheets left behind another, more subtle, and much longer-lasting legacy. Imagine placing a heavy weight on a piece of memory foam. The foam compresses under the load. When you lift the weight, the foam slowly springs back to its original shape. The Earth's crust behaves in a similar way. The Fennoscandian ice sheet was billions of tons of weight pressing down on the land. When that ice melted away, the land began to rise in a process geologists call isostatic rebound. This post-glacial uplift is a slow-motion geological sigh of relief. This phenomenon is not unique to Europe. It occurs anywhere that was once buried under thick ice, including northern Canada and Antarctica. But in Scandinavia, the effects are strikingly visible and are still happening today. The land across this region is rising at a rate of up to 1 centimeter per year, which adds up to a full meter every century. Finland's land area, for example, grows by about 7 square kilometers annually simply because the ground is lifting out of the sea. The process is a direct and tangible consequence of the last ice age. The evidence of this dramatic uplift is etched into the landscape. The ancient shorelines of Ancellus Lake can now be found high and dry, in some places up to 60 meters above the current level of the Baltic Sea. Near Stockholm, some areas that were once on the coast have risen nearly 100 meters. As early as the 18th century, the Swedish scientist Anders Celsius observed this phenomenon. By placing markings on coastal rocks, he was able to prove that it was the land itself that was rising, not the sea level that was falling, a revolutionary insight for his time. This rebound is a process that will continue for thousands of years to come. In places like Hudson Bay in Canada, where the ice was once an incredible 5 kilometers thick, the ground sank by nearly a kilometer and is still rising today. The uplift is expected to continue for another 10,000 years, albeit at an ever-slowing rate. The story of the Channel River and the ice age that created it is not just ancient history. It is a dynamic process whose effects are still shaping our world, a powerful reminder that the Earth is a living, breathing planet, constantly changing on timescales far grander than our own.